our next talk in our section is the talk of Lev Lukutsyevsky, convex trigonometry.
Okay, so first of all, let me thank our organizers for the possibility to make a talk here and also for patience to my strange requests. So today I will speak about a new apparatus, which I call convex trigonometry. And it appears to be very useful in Finsler and some Finsler geometry. Because some differential equations with discontinuous right-hand side appears there, and one need to study singularities of solutions, some non-uniqueness on solutions, and so this apparatus, convex trigonometry, was developed to solve this problem somehow. So let me maybe remind on what is Finsler or sub-Finsler manifold. So we have a manifold, a smooth manifold M, which is rather speakingly similar to Riemannian manifold. So we have, but instead of scalar product at the tangent spaces, we have some norm given in tangent spaces. And this manifold together with this norm is called Finsler or sub-Finsler manifold. In this case, just Finsler manifold. So in usual way, if we are given with some norm which can measure the length of tangent vectors in the tangent space, we can measure length of curves by this standard formula in usual way, and so this norm makes our manifold a metric space, and we can ask usual questions about metric spaces we are asking, for example, in Riemannian geometry. The standard question is the following one. If we are interested in geodesics, for example, yes, so we have two fixed points, x0, x1, and we are looking for a curve which gives a shortest path in terms of length given by this norm. So a standard approach can be applied here. So if we are looking for geodesics, then they are this, and the Hamiltonian in the cotangent bundle appears non-smooth. So usually what we have here, that the Hamiltonian function does not belong to C1. And so the system of Hamiltonian equations. So also there is an interesting subcase when we allow this norm to be equal to infinity on some tangent vectors psi. And in this case, we call the manifold M together with this, together with this norm, we call it sub-Finsler manifold. So for example, if we have in any tangent space, we have a subspace delta of x, and our shortest path must tangent this how do you say, allowed directions in tangent space, and we are looking for a curve of minimal distance that are only tangent to a given distribution in the tangent space. So usually, so the different mathematicians call different objects to be Finsler manifold, but sometimes this what I show here is not called Finsler manifold, but have some other names. But usually everybody agrees with the following: that if you have some modeling norm which models a norm in each tangent space, so that the norm of the tangent vector is given by this formula. So they are somehow similar in different points x on M, but there is some scale linear operator which transforms from the norm from one point to the other. Okay, so I will speak about mostly about Hamiltonian flow of the geodesics into cotangent bundle. But let me show you some examples. Okay, first of all, the simplest Manhattan example. If we have a submanifold M is just a manifold M is just a plane R2, and we have the following norm, Manhattan norm. Then in this case, this blue figure is the unit ball in this metric, and there are a lot of geodesics. Usually there are a lot of geodesics connecting 2 points, so they are shown here. For example, this one is the shortest path. Also, this one is the shortest path, and any curve inside this rectangle, which starts here and ends here and goes to the right. It will be the shortest path. They all have the same length. So as you can see, in this case, the Hamiltonian is super non-smooth. Yes, so there are a lot of different solutions. There are infinitely many solutions, in fact. Okay, so let me show you another less trivial example about about Finsler hyperbolic plane. So let us take the Lobachevsky plane in the model of the upper half plane, but change the usual Riemannian norm by the following some Finsler norm. I remind that in the Riemannian case, the Lobachevsky plane has the following norm in tangent plane, but we change this square root of psi square plus eta square to the following function. Here mu is just a Minkowski function which measure more or less the radius with respect to a set omega. So here omega is an arbitrary convex compact set, for example, like this. In this I show here is a polar set, and hence the omega has the following form. Yes, and in this, Minkowski function is just a radius function which measures this how to say, the scale we need to go from the point psi eta to the boundary of set omega. So this problem comes naturally if you are looking into the Lie group of proper affine linear transforms of the real line. The answer about the structure of geodesics is much more interesting, in my opinion. Here it was obtained by Gribanov in 1999. So to obtain geodesics, we have to do the following. We take the polar set of the unit ball in our metric, and divide this polar set in 2 parts. So left part and the right part, and then we turn the set of omega polar 90 degrees to counterclockwise or clockwise, and obtain 2 types of geodesics. One of them are going to left and represented by the left side of the boundary of the omega polar, and others go to the right. As you can see, in general, geodesics going to the left and geodesics going to the right do not coincide, because the set omega need not to be symmetrical. The unit ball need not to be symmetrical. Yes. So in this case, there is a unique. Usually, there is a unique path. Not usually. Yes, there is a unique path connecting 2 points, x0 and x1, if you choose them. So the Hamiltonian function is not smooth here. The Hamiltonian function of the geodesics flow in the cotangent bundle is not smooth, but the solutions are unique. So to understand what is happening here, we need some apparatus to work with non-smooth Hamiltonian systems given by, for example, 2-dimensional convex sets. So let me show you some problems where this scenario appears. For example, the first scenario of this kind appeared in the Buziman work in 1947. He was studying the isoperimetric inequality on the Finsler's plane. In the modern language, it means that he was studying a left invariant sub-Finsler problem on the Heisenberg group to find exact solutions. And also this study continues by Berestovsky in 1994. Gribanova studied hyperbolic Finsler plane. There was studies, a lot of studies. Nowadays, this is a very, how to say, growing from finite groups by Gromov theorem and from some applications. So here I listed a lot of works which we were able, some of them I was able to solve myself. Some of them we were able to solve by convex trigonometry together with Yuri Leonidovich Sachkov and Andrei Ardentov. So maybe I will not speak about them. There are a lot of applications. We find more than 15 or 20 different problems which were posed in literature and which were unable to solve by mathematician, and which we were able to solve by using the new apparatus of convex trigonometry. So let me show you what the convex trigonometry is. So it is based on the following more or less trivial definition. So suppose that we have an arbitrary convex two-dimensional compact set which contains origin in its interior. So let us introduce new functions: cosine omega theta and sine omega theta. The definition is very simple. So we in the classical case, when we have a circle, when omega do ellipses using arc length, then he obtains the very well-known Jacobi elliptic functions. So what is happening in convex trigonometry? We use generalization by the area. So we take a point on the boundary of the set omega such that the area of this sector is equal to 1/2 of theta, and cosine omega theta and sine omega theta just coordinates of this point p theta. So the definition is trivial. Yes, you can give it in high school, for example, but it appears that using this definition, a lot of properties of the classical functions sine and cosine also hold for the functions cosine and sine with the index omega. But usually in classical case, when omega is a unit circle, you have properties of the pair cosine and sine. But in the general case, this pair, these properties is going to, how to say, so these properties are inherited by two pairs of functions cosine omega, sine omega, and also cosine polar omega and sine polar omega. So we need I need to introduce the correspondence between omega and polar omega, and the correspondence is very similar. So I say that the angle theta in omega corresponds to angle theta polar in omega polar if at this point p theta the corresponding covector q theta polar determines a supporting half plane here. So obviously the definitions to these two functions are completely similar to definitions of functions cosine omega and sine omega. So so here is the reason why I introduced these functions, because we have the following very convenient properties, which are what we are really using while we're solving ODE using trigonometry. For example, obviously, the following generalization of the Pythagorean identity holds. Yes, usually we have here cosine square plus sine square equals 1, but here we should change cosine to the pair cosine omega and cosine omega polar, and so on. The most two interesting things for solving ODE with the discontinuous right-hand side is the following two. First of all, we have these properties for the derivatives of cosine omega and sine omega. So if you are solving a differential equation which somehow involve a convex two-dimensional set, then it is very convenient to use these functions, as it is convenient to use cosine and sine omega in classical Silver case. And also we have a classical polar change of coordinates for these convex trigonometric functions, which is given here. The only difference is that radius, which was square root of x squared plus y squared in singular case, becomes the Minkowski function, which I mentioned is a radius function, which measures radius with respect to a set of. Okay, so these properties are very similar to classical properties of sine and cosine. So let me show you an example of these functions. For example, in case of LP metric, let omega p be a unit ball in LP metric. And so in this case, functions cosine omega and sine omega were studied by Shilupsky. So it turns out that Shilupsky functions are a special case of convex trigonometric functions. So they obey the following very well-known differential equation with discontinuous right-hand side. Let me remember something like this, I think. P minus 2y and y dot equals to modulus x power p minus 2x. So here is some illustrating cosine and sine functions for two squares, two cases p equals infinity, q equals 1. They are easily to compute, any student can do that. Also here I show case p equals 4, q equals 4/3. These functions also can be computed explicitly. This is not a numerical result, this is explicit result. So there are a lot of domains where functions cosine and sine can be computed explicitly. So in this case, we should use beta functions to compute them. So let me now explain how do these functions appear to be useful in studying singularities of the non-smooth Hamiltonian. It turns out that, for example, in a lot of subfield problems I mentioned above, the Hamiltonian system of the geodesic flow. So it has a high dimension, at least 6, so three degrees of freedom. But thanks to these functions, the Hamiltonian ODE, so discontinuous part of the Hamiltonian ODE are always in all these cases can be how to say reduced to the following standard way. So the equation on unknown function, this is just a one-dimensional function, and the equation always have has the following form. Here u of theta is a function f on cosine and sine of theta polar, where f of x and y is an analytic function. It appears to be different analytic functions in different problems. Usually it is polynomial of degree 1 or 2, but it is not important for generic study. So this equation is can be seen as a generalization of the pendulum equation. Yes. So in classical ODE with the continuous right-hand side, Lipschitz right-hand side, we have an equation of the following type. Yes, where u is a potential energy. But in this case, the differential equation is more interesting because functions cosine omega polar and sine omega polar are usually non-smooth and have do not have derivative at corners of the set omega. So this equation has a discontinuous right-hand side and should be studied problem. There are a lot of we may have a lot of problems there because uniqueness. So solutions usually exist due to Filippov theorem, but uniqueness may fail. And so, as in the first example I showed you above, but sometimes uniqueness still holds, we managed to, together with Yuri Leonidovich Sachkov and Andrei Dentov, we managed to study completely the behavior of the uniqueness loss of solutions to the following equation. So first of all, simple proposition that as in the smooth case, this function is a first integral to this equation. It can be seen very easily. So this is a very simple proposition, but in fact, in smooth case, if you have a function theta polar such that this sum is constant, then it is a solution. In the non-smooth case, for the differential equation with discontinuous right-hand side, it is not true in general. But if you have a function that is C1 indeed, and the function is constant so doesn't depend on t, then function theta polar indeed a solution and smooth solution, and t can be found with this standard integration procedure. Okay, so let me show you the picture of the phase portrait for this system with discontinuous right-hand side. So I decided to show you the structure of phase portrait for this very simple function f, which appears in Martinet case, in Engel and Cartan's group. You have so if you write down the Hamiltonian equations of the geodesic flow in these cases, you obtain the following generalization of standard pendulum equation. But as you can see, the correspondence is not one-to-one correspondence. So usually sometimes in the right-hand side you have not a number but the segment of numbers. So this equation has the right-hand side of this equation is discontinuous. But it turns out that uniqueness is lost only on very specific cases. So let us, as we all do on the ODE classes, let us look on the energy levels of these functions u, which is equal f of cosine omega. So in this case we have just this u. So potential energy is the following. So we are going to rise x. So I show here the set omega polar, which is turned 90 degrees so I wanted the energy levels to go up. So at the minimal energy level, we have a set of admissible fixed points. So these points are always fixed, and they give the following interval of fixed solutions. So if we rise an energy a little bit, we obtain a standard oscillating. So we expect, yes, we don't know now where the uniqueness is lost, but what do we expect is that we obtain some standard oscillating solutions. There is a separatrix case when the energy level touches the upper points of the set omega, and we obtain some curves which are these two, so I call them separatrix, but nobody knows exactly what does the separatrix mean in the case when the right-hand side is discontinuous. And if we rise energy a little bit, we obtain the standard rotations. But so as you can see, I pictured here arrows where the motion should go. But in fact, this is just energy levels of the function E. So we do not really know at this moment where the uniqueness is lost. So let me show the theorem, and I will go down to the theorem and then back to the phase portrait. So, oh, I'm sorry, here is a mistake, I think. Something like this though should be written, minus u prime of theta. So we are going back to the general equation of the following form. Generalized pendulum equation for Finsler case. So suppose we are given with some initial data, theta polar of T0 and theta polar dot of T0. So first of all, if the boundary of the polar set is smooth enough, then the uniqueness holds. This is more or less obvious because this function u becomes C2. To be precise, it belongs to the Sobolev space W2 infinity, and so the solution to these equations are always unique. So suppose that the boundary of the polar set is not smooth. For example, we have a polyhedron, a square, or there are some corners on the boundary. And let us look on the different points in this phase portrait. So we start with the point where the derivative is not equal to 0. In this case, due to the theorem 1, the solution is always unique in the neighborhood of this point. So the uniqueness can be lost only in points where the derivative of the function theta polar is equal to 0. But in fact, the third item of the theorem stands that if 0 does not belong to this derivative, then uniqueness holds in the neighborhood of the point T0. On the phase portrait, it means that uniqueness holds in points these points. Uniqueness holds, but here it may fail or may not. It depends. So the first three items more or less stand for the following fact: that in the phase portrait, the uniqueness may lost only at the end points of the separators, but maybe the uniqueness so maybe there is a uniqueness, or maybe there is not. So to study what is happening at the end points, we need the fourth item of the theorem. So and it says the following: that if we are standing at that end points of the separators, then uniqueness is determined by this improper integral. Yes. More or less, it means the following: in the classical case, the time movement on the separators is always infinite, so we cannot touch the end point. But in the non-smooth case, it sometimes happened that the time motion along the separators is finite, that we can reach the end point of the separators in finite time. In this case, the solution have the following structure. So we are going along the separators to the end point in finite time, stands there for arbitrary time we want, and then go down on the other separators, starting from this point. So the time motion is determined by this improper integral. If it is finite, then uniqueness is lost. If it is infinite, then uniqueness holds. So usually, if we have a smooth point of the boundary, for example, here, at this point, uniqueness holds on the separators. At this point, uniqueness lost because we have a corner. This is a complete description of the phase portrait and the singular solutions to the Hamiltonian system. So the singular solutions to the Hamiltonian system with discontinuous right-hand side are exactly these solutions that are standing at the endpoints of separators. Okay. So let me. So this is a result, theoretical result, but we have a concrete formula also. And let me show you some face portraits on the Unimodel for this. So these pictures you are seeing now are face portraits for Hamiltonian flows of sub-Finsler geodesics on unimodular 3D Lie groups. In different for the cases L infinity and L1 on the next slide. So we can write down this procedure, and we obtain for all these cases we obtain exact solutions in terms of convex trigonometry. But for squares it is easy to show the picture. So the face portraits have this interesting behavior. For example, here the time motion is infinite because we have an angle here which is not equal, and here the uniqueness is lost on the end of separatrix because the time motion here is finite. Here are some face portraits for L1 case, also for 3D unimodular Lie groups. Okay, so I finished. Thank you very much for your attention.
No time for questions.
Okay, thank you very much. If somebody has one question, you are welcome. It is very interesting, but not evidently, and it is maybe not possible to understand during one lecture. So if we have no questions, let's thank our speaker. And I think that it was very useful for everybody. Lev, thank you very much.